Cool. Good morning, everybody. So I know Mishra beat me to it already, but I want to welcome you all officially to HashiConf 2019 here. It's super exciting for us to be back here. Amsterdam has kind of become a bit of a second home for our conference. This is now the third year that we've done it in Amsterdam. Let's see. And last year was actually exciting. We did it literally, I think, just across the street from here. That was 2016. We did HashiConf. I don't know why the clicker is stuck here. Oh, here we go. Sorry about that. Technical difficulty. HashiConf 2016 was actually the first time we did an event in Amsterdam, and it was literally at the Transformer House. And it's been fun to just watch the growth of the European user community. At the time, this was the first conference that we did in Europe, and we were sort of thinking maybe we could get 100, 200 people to show up, and we were pleasantly surprised. We had about 300 folks who made it to the first event. As you can see, we've grown a little bit since then. Wouldn't be able to quite fit into the old space. Today, there's a little bit over 790 people, 800 people joining us in total, and then another few thousand people we're expecting joining over the live stream. So what I'd encourage you to do is use this as an opportunity to make new friends, make new connections. For many of you, I think this is probably the first HashiConf. I'm curious, sort of quick show of hands, how many have ever made it to a HashiCorp event, or for who is this? Okay, so then show of hands, first conference for any HashiCorp event. Okay, so this is the first time for a lot of folks. So I'd encourage you, use this as a good opportunity, meet the new people, share ideas. I think many of you will find, maybe you've used Terraform, but someone else here has used Vault, and you can learn about that or one of the other tools. So this is a good opportunity to kind of get together and learn from folks in the community. I think what's been fun is, when we first did our conference in 2016, there were no employees based in Europe. We were probably only about 30 people at the time, totally based out of the States. And today there's now 85 European employees out of about 600 in 6 different countries. At the same time, the user community has grown even bigger than that. So one thing we like to talk about and encourage you to join is the HashiCorp user groups. These are small meetup groups that are local, they're in your communities, and they're really an opportunity to just get together on a regular basis, monthly, quarterly, and just talk about how are you using the tools, how are other people using them, what are the use cases, and it's an opportunity to network in person and get some of that sort of expertise. So these have started, a few years ago was the first hug based out of San Francisco. Today there's a little over a few hundred chapters. There's 28 just in Greater Europe in 16 different countries, and about 25,000 members around the world. Another thing that we're really proud of, we launched this a few years ago, is the HashiCorp Diversity Scholarship. I think one thing that we're sort of aware of is not everyone has the privilege to attend events like these and get to have their travel paid and their tickets paid and get to come and learn from these types of venues. And so our goal was, how do we bring in a diverse community of people who don't necessarily get to attend? So we created this scholarship to bring in folks from both regionally within Europe, but also around the world, people who wouldn't otherwise be able to attend HashiCorp events. And so you'll find people sort of among us who are here because of the Diversity Scholarship. So again, just use this as an opportunity to meet new people, not just the folks you know from other events. So with that, I want to switch gears into talking about sort of what's the HashiCorp mission? What's the kind of ethos for us? What do we sort of focus on and believe in? And I think for us, I can kind of boil it down to one common sort of view, which is our worldview is that everything is going multi, right? And when I talk about everything going multi, I think the sort of obvious one that comes to mind is the world going multi-cloud, right? This is sort of maybe the most obvious version of the world going multi. And I think this is going to not be a surprise for most of the people here. Right? I think over the last few years, we've seen the world kind of go through a few iterations of this. Right? I think cloud in its sort of single form is not really new. I think Amazon EC2 launched in 2006. And so I think we've had this notion of public cloud being around for a while. But I think the long-time view was, hey, small companies and startups, they're going to use Amazon. Large enterprise businesses, they're going to stay on their traditional on-premise. And Amazon is the sort of only cloud. And I think we've seen that evolve over the last few years, where it's not just Amazon. There's many very credible clouds, including Azure, GCP, Ali Cloud, et cetera. And I think the view from large enterprises has also changed. Right? In 2006, it was sort of inconceivable that the enterprise would use the cloud. Now I think when you talk to most large organizations, they all have a public cloud strategy and a multi-cloud strategy. Right? So everyone sort of now adopting everything. Beyond multi-cloud, our view is that things are going multi-platform. It used to be that our applications were largely homogeneous, monolithic applications running on VMs on-premise, and that's changing, right? I think a few years ago, we saw the rise of Docker, which quickly led into container management platforms like Kubernetes. And now we have applications that might span traditional VM-based infrastructure, as well as more modern Kubernetes container-based systems. But already, before we've even finished that adoption process, we're already seeing the frontier shift to serverless platforms, right? And whether we define serverless as sort of function as a service, something like Lambda, or more container as a service model with Fargate and Azure container instances, or sort of a source model like Google Cloud Run, I think broadly you can think about this as kind of a next generation of platform. So our view is that no one of these things will ever be all of your application, right? You're going to mix and match. There's some set of applications, traditional database, it's going to fit best on virtual machine. Some set of application that works best on container. Maybe your new integrations that are lightweight, those will live on serverless. So our view is all of these are going to be a part of your infrastructure. It's never going to be one or the other, right? And then the last piece of this is our worldview is that things are going multi-service, right? Historically, we might have stuck with a monolithic development pattern and had a relatively large single application. And for most users, that's still the right place to start. When you're starting a new project, it's a new company, start with the monolithic app. But over time, as the complexity grows, as the team size grows, that application is going to get split into many different services, right? So we might break up our front end from our intermediate API layers, from our back end storage layers, and this lets us sort of reuse and mix and match different functionality, right? And so as we do this, there's sort of a whole world of operational challenge that we inherit, right? Now we have to worry about how do these services connect to one another, how do we secure it, how do we deploy and manage this much more complex application, where bits and pieces of this might run on different platforms, different clouds, right? And so in our worldview, there's kind of four major groups when we think about sort of delivering an application, right? Our operations, security, networking, and development teams. And for each of them, there's a set of assumptions that changes as the world goes multi, right? I think for sort of operations, we used to live in a world which was very consistent, right? It was dedicated servers, largely physical and virtual machine. That's going away, right? Now we're going to have capacity on demand. We're not going to have 100 machines that we bought and racked and stacked. We're going to scale up and down as needed. And it's going to be a mix of different types of infrastructure, virtual, container, function, et cetera. For our security teams, there's a total shift in their model, right? I think historically the security model is what I like to call kind of castle and moat. We had sort of the front door that we brought all of our traffic over, and we put our firewalls and our web filters and our intrusion detection systems there. And we basically asserted that the outside was untrusted and insecure, but the inside was trusted and secure, right? So sort of the castle walls defended us, and we trusted everyone on the inside. But as we go through this shift to multi-cloud, multi-platform, multi-service, it gets much harder to secure that inside, right? It's not clear where the walls begin and end because I have now 5 different data centers and 5 different cloud environments. What's the front door? All of these things are connected to one another. Traffic's flowing back and forth. So as we kind of transition, we start to lose this notion of a clear perimeter. It's not obvious anymore what the traffic flows are. And so we change our security model from saying everything inside is trusted to instead we're going to assign an identity. Every application, every service has a unique identity, and we're going to use that to govern access. This is the notion behind sort of zero trust networking or identity-based networking. Then when we talk about sort of connecting these different services together, traditionally we took a very host-oriented approach, right? We had a load balancer that pointed to the set of machines that were web servers or pointed to the set of machines that were databases. But now as we sort of transition into this multi-platform, multi-cloud world, what does it mean if we don't even have a machine running behind it, right? How do I point to a Lambda, right? Maybe it's not even running. Until I invoke it, there is no IP. There is no static machine running there. So the whole notion of how I think about routing and networking has to reorient not around hosts and machine, but around logical service, right? Maybe until I invoke that service, it doesn't even exist. And then lastly, the way we think about managing and deploying our applications has changed. Historically, we thought about sort of physical dedicated infrastructure. These 50 were a web server, these 10 were a database, to now saying, you know what, I have a 100-node Kubernetes cluster. I don't really know what's running on any particular machine. It's dynamic, it's ephemeral, things move around. We're going to schedule across a dynamic fleet rather than statically managing many different smaller fleets. And so I think if you zoom out and look at the sort of cloud landscape, these problems have all been solved with a variety of different tools, right? Within each cloud, within each environment, there's different approaches to this, right? Whether, if we're talking about provisioning, I might use CloudFormation in Amazon, I could use ARM in Azure, I could use Deployment Manager in Google. Each of these provides sort of a way of doing an as-code provisioning process. But if I'm operating in a multi-cloud, multi-platform world, I don't want to have to be exposed to the sort of full complexity of this entire matrix, right? I don't want 5 different tools for the same workflow. And I think that's really the kind of ethos behind the HashiCorp portfolio, right? Our view is that these problems exist across all these environments, across all these platforms, but how do we have a kind of a common workflow, a common way of doing it, whether it's provisioning, whether it's identity-based security, whether it's networking, whether it's the way we deploy our applications, right? So that's kind of how we think about the tools in relation to each other and the clouds themselves, is it's really about providing that common way to operate in this environment. So I think one of the interesting things when we talk about sort of this mixed platform, this mixed mode, is that in some sense this is not new, right? If we go back as far as you want to go back, right, to mainframes and then scrub forward from there, you'll find organizations that still use all of these technologies, right? Go to any large bank, and at the center sits a mainframe. Around that is the bare metal, around that is the VMs, around that is the Kubernetes environment, and around that will sit the serverless stuff. It's sort of like rings in an old tree, right? And so when you talk about what's made this possible, like how have they been able to mix and match 40 years of different technologies, it's ultimately about the fact that there's a common network, right? The new serverless application can communicate with the mainframe because they both speak TCP. Right? They both get an IP address, they both speak a common protocol, and so in this way the network has been sort of the common denominator. It's been the piece that's allowed all these technologies to interoperate and sort of shielded the fact that it doesn't really matter if one app is in a container and one app is in a VM, as long as it has a network IP and it speaks the right protocol. And so I think there's always been kind of 3 key challenges that we've pushed into our network and thought about as a networking problem, right? One of those is naming, one is authorization, and one is routing. So we'll touch on each of these quickly. So when we talk about naming, it's really about what is the address, what is the sort of logical name my downstream uses to talk to my upstream. So in this case, my downstream web server wants to talk to my upstream authentication service. What's the name that the web server uses to reach it, right? What is it hard code as the URL string? And I think historically the approach was static IP, right? So in this case, the .51 IP would be the name that the web server is using to reach the authentication service. What's common is you end up using something like a load balancer or as a virtual IP to do that sort of disintermediation. So .51 isn't actually an instance of the authentication service. It's taking us to a load balancer. The load balancer is then acting as the name, right? And it's connecting back to one instance of the authentication service, right? So this is a common problem. Another common challenge is doing authorization, right? So the way we typically see this solved is putting something like a firewall into the network in between the path. So if I want to have authorization around who's allowed to talk to this service, I might put a firewall in front of it and then manage a set of rules, right? So I can say .51 is allowed to reach, .104, and the firewall is now acting as an authorization function, right? The final piece is routing, right? And routing is sort of a big world. There might be many different reasons you're doing routing. You could either be doing it for load balancing, right? Maybe I have a lot of traffic and I need to run 10 instances and I want traffic to split across it. I could do it for high availability. So maybe I have 2 instances of my database, my primary and secondary, and I don't want to overwhelm one of them. Or I'm doing it as a failover mechanism. And the other use case might be more sophisticated things like canarying of traffic, right? So in this case, maybe I have 2 versions of my app, version 1 and version 2, and I want to send some percent of traffic, maybe 1%, to version 2 to understand, does version 2 work? Are there bugs? Is it performing the way I expect? And then if that looks good, I can sort of crank up the amount of traffic that goes to version 2, right? So all of this I'd loosely put into the same category of routing. And here's where you would again see a pattern like putting a load balancer in the middle. So what this allows us to do is not burden the downstream with the logic of this sort of routing, right? I don't want my web server to have to know about traffic shifting to its upstream or dealing with multiple versions, et cetera. We sort of shield it, let it talk to the load balancer, and move that logic out of the application, right? So this is sort of common. So if we look at kind of a traditional data center, what you'd see is a very clean north-south path, right? Internet traffic comes in from the north. It flows through our perimeter firewall. This is how we make sure the untrusted bad things stay out. The trusted good things are on the inside of our four walls. From there, we probably go to a front-end load balancer, which brings us out to our web servers. They do some processing and ultimately are reading and writing data from a back-end database, right? So the back-end database is probably shielded as well with a firewall that prevents services that shouldn't reach it from talking to it, right? This is sort of the traditional data center. And here we have to probably manually manage things like our firewalls and load balancers. Now, as we sort of extend that and go to multi-data center, you might say, okay, now I have a cloud region, right, that I'm going to add onto this. That needs to connect back to on-premise with some form of networking technology, whether it's VPN, SD-WAN, dark fiber, etc. Right? There's some networking link back between these zones. And I might adopt a newer platform, right? And this goes to the sort of multi-platforming we see, is one might be my more legacy environment, one is where I'm adopting Kubernetes for my new microservices. And so there's going to be some new databases that exist in the cloud. My new services might use, key value store, might use a graph store, etc. But very likely they need to communicate back to the existing on-premise environment, right? I need to reach back to old data, old services. And so I need to manage names in a way that are portable between environments, authorization in a way that's portable, routing in a way that's portable. And this problem sort of only gets worse as we get bigger, right? The bigger we get, we start adding more data centers, sort of an explosion of network linking in between them. It's not just one VPN tunnel now. Now you end up with 8 different tunnels or 16 different tunnels as you start scaling, and even more platforms, right? So the complexity sort of grows. So it's in this environment that we really designed Consul, right? So our goal when we talk about Consul is really talking about solving the service networking challenge, right? And so these are kind of the key challenges. And so within that realm, there's sort of 2 key ways to think about Consul. One is as a traditional service registry and discovery mechanism, and one is as a service mesh. And when we talk about this, we don't think about them as being sort of a binary distinction. It's not one or the other. I think it's part of a sort of a logical maturity journey of the network, right? I think if you look at most networks, where most users start is centralized hardware, right, running on-premise with a manual process around it, right? So I file a ticket and someone logs in and updates my firewall, updates my load balancer manually. From there, I think the service discovery journey is really about automation of that process. So I can keep my centralized hardware, but now I move away from manually managing the load balancer, manually managing the firewall, to allowing it to be automatically updated based on logical rules, right? From there, as we say, great, I want to adopt a public cloud environment, I'm not going to ship my hardware device up to Azure, right? So how do I change my approach? I move from a hardware-based approach to a central software approach, right? Think about running like Nginx as your front-end load balancer instead of F5 big IP. Right? So it's fundamentally the same sort of logical model. It's a centralized appliance, but we're moving from hardware to software. How do we still do it in an automated way? And I think the final evolution of that is moving away from central appliance, right? And pushing that out to the endpoints of our network and doing it with a distributed software approach, and that's what becomes the service mesh. So in this way, we don't think about it as a binary one or the other. It's part of a journey, and in fact, you're probably going to have a mix of all of these things in your network at the same time, right? So when we talk about service discovery at its core, it's really about using a name as a name instead of an IP as a name, right? So the web server, instead of using the .52 address or the .104 address, would use a logical name like auth.service.consul. And then that's getting resolved dynamically into a physical address, right? So in this way, we can scale up and down. We can have different IPs. If that instance fails, we can resolve it to a different node. And so it's really about sort of moving the naming function to something that's dynamic. When we talk about the network automation piece, instead of managing those sort of static firewall rules that said .51 can talk to .104, we instead manage sort of a logical rule, right? We say the web service is allowed to talk to the authentication service. The set of IPs, though, are dynamic, right? So we don't know which set of IPs are web services because maybe we're scaling those up and down. And same thing with our auth service. So what we do is allow Consul to act as that dynamic registry and knows what set of IPs are web, what set of IPs are auth, multiply those together, and that becomes your firewall rule, right? And so if I boot a new web service, I scale it up and down, I have it in an auto-scaling group, etc. Now the firewall can be updated on demand. I don't need to file a ticket and someone manually adds a new IP rule. We can sort of automate the flow in the middle of the network. And when we get to sort of the final version of this, what we're really doing is pushing that functionality to the edge of the network, right? So what we might have is something like Envoy running within our pod, within our VM, as a sidecar to the application itself. And so what happens now is the web server, when it wants to discover and connect to its upstream, it's really talking to the local Envoy instance. So the name is always local. The local Envoy is doing the routing. It's determining where's my upstream, how do I get to it, what % of traffic should go where. And then the upstream Envoy is responsible for authorization. So when the connection comes in, it determines whether or not that client is allowed to talk to it. So in the same way, that networking, authorization, and routing function still exists in the network, it's just been pushed to the edge, right? And so sort of summarizing at a very high level, I think the goals for Consul are sort of threefold. One is to be API driven, right? We want this to be pluggable with your deployment process, your CI/CD process, the way your network should be automated, right? But we also want to acknowledge that the world is going to be multi-platform and multi-cloud. Very unlikely that you'll ever be able to standardize on one technology that's forever future-proof, right? And the other side of this is really thinking about what's the orientation of the network, right? I think, if you ask some vendors, the network is the center of the universe and everything else revolves around that. Our view is the opposite, right? The application is the center of the universe. Everything else revolves around the application, right? So how do we get the network really to be, in some sense, a detail? What we want to do is manage the high-level intentions of, great, the traffic should be allowed, or we should do a failover between data centers. And then the network should just be automated to support that. So as apps come and go, get scaled up and down, that becomes sort of a detail that gets automated away. It's not the primary focus. Right? And so with that, I'd like to introduce Mitchell Hashimoto, co-founder, to the stage to talk more about the Consul updates we have for you.
Cool. Thank you, Armon, and hello, everyone. So Armon did a great job of framing the problem and showing the importance that the network plays in being able to really manage these multi-platform, multi-cloud, heterogeneous environments. And I'm going to overlap a bit with Armon. I'm excited to talk about the work that the Consul team has done. I think it's really amazing. But I first want to just review what we announced last year, right here in Amsterdam, because we've been building on top of that. So last year, we announced a feature in Consul called Consul Connect. And Consul Connect, in one sentence, enables secure service-to-service communication with automatic TLS encryption and identity-based authorization that works everywhere. I went in detail last year and explained all of this. This year, I'm just going to show a quick diagram just to get us back up to speed. This is similar to what Armon talked about, but simplified. What the world before Connect was very much like this. You viewed things at an IP level, and when one service wanted to talk to another, you would reference the other IP, make the connection. This happened usually through a firewall, and this also usually happened with plain TCP. It was usually plain TCP simply because managing TLS is quite difficult. You have to think about how you protect keys, how you rotate keys, how you issue certs, how you distribute certs. There's a lot going on. So typically, this is what you would see in most data centers. Unencrypted traffic using IPs to route from one to the other. With Connect, what we did was allow you to view these connections at a more logical service level. So instead of saying IP1 to IP2, you would think about it in terms of API to database. You would use the service names. The IPs still exist, of course, because that layer of the network still exists. But from a connectivity standpoint, it's mostly invisible and automatic to the user. This all happens over mutual TLS, because Connect and Consul are managing the CA for you, issuing certificates, handling the rotations. All of this is automatic. And you're able to make rules that instead of IP1 to IP2 is API to database, or say more explicitly, web cannot talk to the database. And you could enforce this even though API and web share the same machine, share the same IP. And so this is Connect, and it's what we announced last year. It's been working great. We've seen a lot of users adopt it. And we're really excited about it. We've been improving on it. But there's still some challenges. One of the major limitations of this model is that the things at the end of the day still have to be routable. Your API service, when it translates down to an IP, and your database service, when it translates down to IP, still have to have connectivity. So they usually have to live in the same VPC or the same subnets or something like that. And with this multi-platform world, this is more and more becoming untrue, even at sort of simple levels. So the most common case is that you're running multiple regions, multiple VPCs, maybe in the same cloud platform. And now, this isn't free. You don't automatically get access from API to database. You have to somehow set up the connectivity between these two things to make this work. Where this is becoming very apparent is in deployments such as Kubernetes. Kubernetes generally wants an overlay network. So Kubernetes, within its one cluster, has nice full connectivity, but as soon as you want to connect either to a VM outside of it or another separate Kubernetes cluster that you might have, this problem arises, and it gets very difficult. And so this sort of thing is happening earlier and earlier. It's not just a big company problem. It happens as soon as you basically adopt a Kubernetes service. And this is a solvable problem. This isn't an impossibility, can't be solved with the technology we have. We have the technology today to solve this, but the challenge is that you essentially require a networking professional that really understands how to set this stuff up. And the process to set it up is typically very manual and labor intensive. And so common approaches to make this work today may be things like VPN tunnels, IPsec tunnels. If you're doing hybrid cloud, private to public, you might be setting up direct connect, direct fiber between different data centers. There are answers to do this, but it does get very difficult. There's also another scenario that Kubernetes tends to introduce to make this even harder, which is that by default, many hosted and on-premise Kubernetes distributions create the same IP space for their overlay networks. So instead of having 10.0.1.1 and 2.1, you actually have the same IP space on both sides. So now you have two pods in two different clusters that actually have the identical IP address, and how are they supposed to communicate to each other? In this scenario, things like VPNs no longer work, and you have to do something a little bit more creative. So again, tractable problem, theoretically solvable problem, but practically very, very difficult, and haven't seen it happen in the wild. For larger companies, the problem gets much worse, and so this scenario becomes quite realistic. Over the past year, I've talked to more than a dozen of our users and customers that this is exactly the scenario that they're in. They have a traditional on-premise data center running something like vSphere. They have some VMs in a cloud, such as Amazon or Azure, and now they've adopted a platform like Kubernetes. They're all running separate networks, and yet they want connectivity between all of them. Again, between the on-prem and VMs and cloud, you could typically set up something like a direct connect. The challenge with that is it goes 0 to 100 really fast. I mean, setting up a direct connect is an extremely expensive, and you really have to make that investment to make it happen. You can't just try it out, right? This is very difficult to set up. The other challenge is there's no consistency between this. You could do direct connect between your EC2 and VMware. That's not really going to automatically work between VMware if your VMware VMs want to talk to your Kubernetes pods. So you have to do something different for that, and you have to set this all up. So this becomes very difficult. So as a solution to this challenge, we've built, and I'm excited to announce, a feature called Mesh Gateways into Consul. In one sentence, Mesh Gateways are a feature that enables secure service-to-service communication built on top of Connect that enables us across networks, maintaining complete end-to-end encryption that also works everywhere. And it's all automatic. So let's go back to this challenge that I posed earlier, this simplified example where you just have two different networks. The way this would work in a mesh gateway world is like this. So you would deploy a mesh gateway device, just software, onto the borders of your networks. These could be VMs, they could be containers, they could be anything. The only requirement is that these deployments could talk to both the private network as well as the external network. And once you deploy them, Consul sees that and automatically routes traffic through the gateways across to the different networks. By having these gateways be limited, you could set up direct firewall rules so that one gateway could only talk to another gateway, so you don't have traffic free-flowing on the public internet or going anywhere. You could lock this down so that only your regions and your edge devices could talk to each other, and that enables all of your services within each region or data center or platform to be able to communicate. And when you do this, the security is maintained throughout. So from API to database, it's encrypted all the way through. The mesh gateways cannot and do not decrypt the traffic. They just route it to the next place that needs to go. I'll talk more about that in a second. Going back to the more complicated scenario, it now just looks like this. For every single region or network that you have, whether it's 3 up to n that you have, you run a gateway device on the edge of each network, and now you have complete connectivity across every region globally. The magic of this is that it really just makes it seem flat, right? Your service, from a developer's perspective, when it wants to talk to a database, they don't need to worry about where that is, how to get there, anything. You just say the same thing, database.service.consul. You connect to it, and Consul handles the complexity of getting that routing to the right place, maintaining security throughout, etc. And as I said before, the problem was solvable, the problem was tractable, but the issue was that it was very complicated. So our goal was not just to make this work, but to make this work easily, magically, automatically. And so the way this ends up looking in Consul is like this. You run a built-in command. In this case, it's the Envoy command, because we're going to use Envoy. This starts up a mesh gateway, and all you have to do to configure it is give it a private address to listen on, and then a public address to listen on. And with just this configuration, it'll register with Consul. So Consul service registry is now aware the gateway exists. And when API wants to talk to database, Consul knows database is in a separate data center. Consul has been data center aware with services since it first came out 5 years ago. And when it knows it's in a separate data center and it sees that a gateway is registered in its catalog, it begins routing traffic through that gateway. If you tried to connect to a service that was within the same data center, it connects directly to the service, does not use the gateway. You could also run multiple of these, so for high availability regions or to balance bandwidth across these gateway devices, you could run as many of these as you want to. They're stateless devices, so you could run 2, 20, 50 if you wanted to. You could do whatever you need. You could also set up configuration of whether services should or should not use gateways. So it doesn't need to be global. You could say some services can use the gateway. Other services, I never want it going through a gateway across the data center. And you could do this on a service-by-service basis. This isn't completely obvious, but what I'm doing here is configuring the defaults for every single proxy, connect proxy that we have set up. And I'm saying that the default should be to always use the gateway devices for traffic. In addition to building the core feature set, the Consul team has done a good job of enabling gateways with other things in the Consul ecosystem. For example, right away, we have support for gateways in the UI. So if you found a service that was a gateway in the UI, you'll see next to the name that there's a label that notes that this is a gateway. And you could also click the IP addresses to see what its external addresses, what its local addresses, and what its data center specific addresses might be. All right, so let's talk a little bit about the details of how this works, so it's not magic. As you might have figured out from the previous slides, the gateway proxy is just Envoy. And so it's really important to understand, and I explained this last year, that Consul and Consul Connect is a control plane. It handles the configuration, the metadata, issuing certs, getting that data, but the actual bits flow through the data plane, and Consul doesn't do that. Consul is a completely pluggable data plane. So we have built-in support for Envoy, but Envoy is just implementing a public API. So anything else could register as a proxy, and it could also register as a gateway. And you can mix and match these. So you can imagine that the gateway device for your on-prem data center may actually be a hardware device. That hardware device could integrate with Consul's APIs and act as a mesh gateway. But in the cloud, you might just use the built-in Envoy software, and that would be there, and you can mix and match these things. From a security perspective, as I mentioned previously, gateways not only don't see your payload, but they cannot decrypt the payloads. So we maintain full end-to-end encryption. There cannot be any man-in-the-middling happening for this traffic. The way we do this is that the gateways do not have access to the private keys to decrypt the data. The routing works by just inspecting the SNI headers, which just say something like database dot, some data center, like it's what you're trying to reach. And besides that, they can't actually decrypt it. The only thing that has the private keys to decrypt the payload is the end service. Additionally, intentions, which are the rule system that Consul uses of what services could talk to others or cannot talk to others, are enforced across data centers. So you're able to set up rules such as allow API to DB and deny web to DB, and you don't think in terms of data center. It doesn't matter where DB is or web is. As you move these things around, as you move it from on-prem to cloud or vice versa, your rules and your security remains enforced. So even if it has to route across data centers, it's all enforced. And so the amazing thing about these mesh gateways and Connect in general is sort of the separation of concerns that it can enable. For a developer, they don't need to think about routing. They just talk to whatever service they need to talk to, and Consul handles that for you. For someone like an operator who's setting up these clusters, as long as they configure the gateways correctly, then the entire world is flat. Anything could talk to anything, and it's there. And then for someone who's more concerned about security, there's a central intention system that says what can and cannot talk to the others, regardless of where it's deployed. And so you create these nice separation of concerns that could be focused on a specific problem set, but all work together to sort of enable what each group wants. And mesh gateways are an open source feature, and they're available in Consul 1.6, which has been released for beta today. So the Consul team's done a great job. I think that itself would be an amazing announcement, but they've done more. So continuing to build upon Connect. I'm excited to announce that Consul has completed the much-awaited Layer 7 features completely. So today, routing in Consul looks like this. You would request a web service, and Consul looks up the healthy instances and returns them directly to you. This is unchanged if you do nothing and upgrade Consul, but we've introduced a number of new features. So with the new Layer 7 functionality, service discovery can now look like this. I should mention that each box that I introduced in the middle is totally optional. You could have one and not the other. You could have two but not three. But if you wanted to do the full path, this is what it would look like. So I'm going to walk through an example of what's possible with Consul now if we had everything enabled. Let's start with HTTP routing. With HTTP routing, you can now configure in Consul Layer 7 HTTP routing rules based on request path, headers, query parameters, and HTTP methods. Following this example, I'm going to configure some routing rules for our web service. So what I'm doing here is configuring a router for the service web, and then I'm setting up a bunch of routes. In this case, I'm saying I want to match an HTTP request, and when the path prefix is admin, I want to rewrite the destination to actually the service admin rather than the service web. In addition, I want the prefix to be rewritten to slash. So when this HTTP request hits the admin service, we get the prefix stripped. So if you said go to web.com/admin/users, it would actually go to the admin service, and it would only see /users. And so what ends up happening is we requested web.service.consul. That matched that routing rule, and so it redirects admin to service admin and pass slash, and now it enters the next step in this discovery chain, which is traffic splitting. With traffic splitting, we're able to set weights and redirect traffic between multiple subsets of services that are deployed. And so, continuing this example, we're now configuring the admin service, because remember we were redirected from web to admin, so Consul is going to look at the traffic splitting rules for admin rather than web. And we're setting up some splits. And the splits in this case are saying send 10% of traffic to version 2, 90% of traffic to version 1. Pretty simple, I think. And for this example, let's say we hit the 10%, 1 in 10 dice roll, and we got subset v2. So we came in as web, got redirected to admin, got split onto the v2 path, and now we hit the step of custom resolution. So think of resolution in Consul before as simply find all healthy instances and return them. You can now customize this logic that Consul uses and to do a number of different things. You could say find healthy instances that match with certain metadata keys, find unhealthy instances if you want to. You could fail over to other data centers if no healthy instances are available. You could customize this resolution logic. For this example, we're just going to set up resolution logic that knows how to route this v1 and v2 subset. So what we're doing here is creating a service resolver for, again, the admin service. We're saying the default subset, if none of our filters match, is v1, assume it's v1. And then we create the filters in order to assign it to a subset. And so we say the v1, you're assigned to the v1 subset if you have a metadata key of version that's equal to 1, and you're the v2 subset if you have a metadata key of version equal to 2. And these filtering rules could be pretty arbitrarily complex logic on a number of different fields within the service. So you could do tags, you could do metadata. It could get pretty complicated if you wanted to. With that, we know that we're looking for metadata version equals 2. And finally, at the end of the chain, Consul looks for those instances, looks for the ones that are healthy, and returns those all the way through. And so in this example, we started requesting one thing, and because of the HTTP routing, traffic splitting, and custom resolution, it completely changed the results that you would get by default. And again, all of these boxes are totally optional. You could have just traffic splitting on with a normal connection. You could only have custom resolution just to do failover. You could set up just basic HTTP routing to set up simple routing between different services, or you could use them all together. And of course, this seems kind of expensive, right? Like if every single request to web had to go through this entire chain, that's kind of a lot of things to do. Consul is much smarter than that. We could rely on our agent-based model, and what we actually end up doing is on each agent at the edge, when the first request comes in, we do this, and then we set up a edge-triggered cache within that client, so that from that point forward, when any of these rules change, we push the new results to the client regardless of if there's requests coming in, and so that every request going forward from that is effectively free. It's just looking up in a table of where to route to. And then if we don't get requests for a certain amount of time, it drops off the cache and you get all that back. So this is how this works. It's effectively free for high traffic scenarios, and that's thanks to our client-based agent model. And just like mesh gateways, all of this functionality is available open source in Consul 1.6, the beta that's available today. And finally, for Consul, I want to talk about Consul and Kubernetes. So Armon mentioned the realities and the importance of a multi-platform world. Kubernetes is quite a large platform in that ecosystem. And with Consul, we've been integrating deeply with Kubernetes, but one of the first questions is, what does that mean? So Kubernetes provides a number of the primitives that Consul does on the surface. It has discovery through functionality such as services, kubedns, kubeproxy. It has service configuration using things like config maps, and it has some limited set of segmentation using network policies and controllers. The challenge is this generally only works for Kubernetes, and worse, it usually only works for single cluster Kubernetes. So even if you're pure Kubernetes and you have 2 clusters, these don't magically work together. You have to figure out a way to set up federation, which doesn't quite work yet, and it's difficult to do. If you have something that is non-Kubernetes, then this is mostly off the table. The goal with Consul is to unify everything. This is the works everywhere point that we make in all our sort of descriptions of our features. Consul works with Kubernetes, it works with cloud, it works with VMs, it's multi-datacenter, multi-cloud, etc. And importantly, it exposes these features in a consistent way across all these different environments. But of course, we don't just want to say it theoretically works, right? It's just a binary, you could run it anywhere. It's important to integrate with those ecosystems in order to make it feel natural. So what we've done with Consul is, for the past year, we've had a project called Consul Kubernetes that provides first-class native integrations with Kubernetes to enable many of these features of Consul to work in a consistent way. Some of the features, I won't go into detail, but just to highlight some of the features that are available now with Consul and Kubernetes. We've had a Helm chart, an official Helm chart, so you can install pretty much all of Consul's features directly into Kubernetes. We have something called an auto-join provider, so that if machines outside of Kubernetes want to join a Consul cluster within Kubernetes, they don't need to know Kubernetes APIs, pod IPs, how to route to them, anything. They just say it's in Kubernetes, and here's the roles and filters, and it just goes and finds them and joins them for you to form the cluster. We do catalog syncing so that you could continue within your Kubernetes environments to use first-class Kubernetes services, which are automatically synced into Consul catalog for external services, and vice versa. External services are synced into Kubernetes service objects that they could use internally to route to all these different services. We do connect auto-injection so that your pods automatically get the connect proxy injected into them so they could use the connect functionality. They don't need to manually start up Envoy or anything like that. From a security standpoint, a challenge with something like Consul is we have an ACL system in Consul, and the question is, how do I get an ACL token to talk to Consul? With the past couple releases, you can now authenticate to Consul just directly with a Kubernetes service account, so you don't need an ACL token. We automatically do that auth for you. And there's also automatic TLS. So if you're in a Kubernetes environment or otherwise, automatic TLS can be enabled so that all the clients talk to the servers over TLS with all the certificates automatically managed. Now, this is a cool feature that we've been able to build on top of Connect internally. So even if you're not using Connect externally, the Consul cluster itself could leverage its own service mesh capability to do automatic TLS for all its private communication. And then, just like UIs, the Kubernetes team with Consul has done a great job of integrating mesh gateways right away for day one release, and so they work right away. The way the mesh gateways would work is you check out the latest version of the Helm chart, and you set some configuration. And this is the minimum configuration you would need. You say enable mesh gateways, you set the number of replicas you go on. Again, this is for high availability or just more bandwidth availability on your gateways. And then you just tell us what the outside external address to talk to this gateway is. You run your Helm update or Helm install, the gateways are deployed, and all your traffic within Kubernetes can now talk to any other network. And I mentioned this earlier, but a really important use case for this is multiple Kubernetes clusters. So even if you're pure Kubernetes, you could set up mesh gateways now and have your pods be able to route with full service HTTP routing, traffic splitting, custom resolution, automatic TLS, authorization, all included across Kubernetes clusters, even if the two pods have an identical IP address, right? You could have the same overlay on both sides, and this still works. And so this is a really, really sort of magical and important feature to enable, again, sort of making the world seem flat and making your services just be able to connect to each other. And so it's really fun to talk about all these new features, but it's also important to hear from real users about how they're using our software. And so in order to do that, I would like to invite to the stage Laurent from Datadog to talk about their usage of our tools. Thank you.
Hello, everyone. I'm Laurent Bernaille. I'm staff engineer at Datadog, and I'm very happy to be here today to share how we do service discovery in our infrastructure and the challenges we face. I'm going to do a very quick introduction on Datadog if you don't know who we are. So we're a SaaS-based monitoring company. We do metrics, APM, and logs, and other products such as synthetics and many other products in the works. We have thousands of customers, hundreds of integrations, and just to give you an idea of scale, because this is where part of the challenges we have are coming from, we process trillions of data points per day, and to do that, we have tens of thousands of VMs. And to make it even more complex, we are migrating from virtual machines to Kubernetes, which makes it even more challenging, as we're going to see just after. Before diving into service discovery and the challenges we face, just a quick intro on how we've been using HashiCorp software for quite a long time now. So first of all, we use Terraform and Packer heavily. So we use Packer to build all our base images, and we use Terraform to configure all our cloud resources across different providers, such as AWS and GCP. And today we have thousands of Terraform files, and it represents tens of thousands of lines of Terraform code. So we really rely heavily on these tools. We also use Vault pretty heavily for secret management. And I'm just going to focus on Kubernetes to just give you an idea of size and scale. So in our Kubernetes cluster today, we use Vault to get secrets and to provide PKI services. So all our control plane services retrieve certificates using Vault. And as you can see, we do like 100 certificate signature per hour or something. And we also heavily read secrets from Vault inside Kubernetes, because every time a pod starts, it's authenticating using its Kubernetes service account, getting a token from Vault, and then getting secrets. So let's dive now into service discovery. So as I was saying before, we have both virtual machines and Kubernetes clusters, and this makes service discovery very challenging. So this is a quick representation of what we have. So before Kubernetes, we had a large set of virtual machines, like tens of thousands, and service discovery was local to this set of machines. And now we are migrating to Kubernetes, so we're introducing Kubernetes clusters. And because we have such a huge scale, we cannot have a single Kubernetes cluster, so we have multiple ones. And also, we're providing our services in different regions. So we have these different infrastructure, virtual machines, Kubernetes clusters, across different cloud providers and different regions. And this raises quite a bunch of challenges. So the first one, for instance, is imagine your workload running in cluster 2, so the B hexagon in the diagram, and you want to reach a service that's on a VM. In that case, you can't rely on Kubernetes services, which is what we use inside the cluster. So we need a solution to find C, for instance, to find A, sorry, for instance. Another example would be you're in a VM in cluster in the classic VMs, and you want to reach a service inside Kubernetes. So, for instance, you want to say, where is C? And you can see that like normal service discovery inside the VM is not going to help you find a service that's running inside Kubernetes. And we also have the issue between clusters, of course, because when you're inside Kubernetes cluster, you have all these nice features for service discovery built into Kubernetes, but it doesn't allow you to do cross-cluster. And even worse, sometimes you have services that are deployed across different clusters. And this is the B example on this diagram, where when you want to reach B from A, you're actually reaching services that are spanning 2 different Kubernetes clusters. In addition to that, sometimes we have requirements when we need encryption and authorization, which makes it even more challenging. In addition to these features, we have very big scalability challenge. So just to give you an idea of what we need to be able to achieve, we need to be able to address thousands of services, tens of thousands of nodes, and hundreds of thousands of pods. So this is large figures, and this is very tricky to make it work. So the first thing is we need the control plane to be efficient. Because as you can imagine, if you're distributing this topology, this complex topology information across all these nodes, you want it to be fast. So for instance, if an application is going down, you need the endpoint to be updated very fast all over your infra. So you need, to be fast, like a few seconds. And also you need the traffic generated by a single event of this type to be small enough not to overload the control plane. And finally, you can't get all the topology information on all nodes, because otherwise it's going to consume too much memory. Imagine if you have an envoy running on each node, and this envoy has a full view of the whole topology. You can imagine how much memory it's going to use. In addition to control plane efficiency, we also need the data plane to be efficient. And by that I mean we need the hover rate during service-to-service communication to be low enough so it doesn't impact our application. And as you can imagine, in our case, the volume of traffic we get is pretty heavy. So here is our approach, how we've done it in the past, and how we're doing it today, and what we plan to do in the future. So before migrating to Kubernetes, what we were doing is we were deploying a Consul agent on every node. And so every services were discovering themselves using Consul, and that was working pretty fine, even if it was sometimes challenging given the scale we were running at. In Kubernetes clusters, we use Kubernetes services, which is a logical and simple way to do it. However, we also need to solve the issues I was mentioning before. So for instance, we need to address services that are running on instances. And for this, what we do is we use Consul DNS. So we run Consul agent inside Kubernetes, and we use Consul DNS to risk services running on VMs. But we also need to solve cluster-to-cluster communication and VM-to-cluster communications. And to do that, the way we do it today is we rely on ingresses and DNS. So basically, we publish DNS services and cloud provider DNS, and we access these services, and we use that as ingress. So it kind of works, but it doesn't solve all the issues I was mentioning before. There's no authentication, no encryption, and using DNS this way to do service discovery is not very efficient because propagation time can be a bit long. So in the future, what we plan to do is to do service mesh to solve all these cross-cluster communication and VM to cluster communication. And we're really looking forward at all the features Michel announced before, because they should be able to help us solve these issues I was mentioning. So in conclusion, as you grow and as your topology gets more complicated, service discovery is getting pretty tricky. And so we really believe that service mesh is a good answer to this question, and that we're really looking forward into new solutions and efficient solutions to this problem. And now I'm going to welcome back Michel on stage.
All right, thank you, Laurent. So that concludes sort of the features that we have announced for Consul. And so with that, Consul is now really a completely full-featured service mesh solution. It's also the first service mesh to support these multi-cloud, multi-region, multi-platform deployments in a completely automated fashion. So we've been discussing the challenges of service networking, and I'd like to continue that with a few features that we have for Nomad as well. The first feature is that we're introducing network namespace support into Nomad. Network namespaces enable us to have an isolated network for every task group within Nomad. And so what this ends up looking like is that for your group, say in your app, you can now define a network, such as a bridge network, and this creates a private network namespace for all the tasks within that group. You could set up port forwarding so that you could define an HTTP port. In this case, Nomad will create a dynamic port such as 1234, and when that's reached on the host machine, we'll route it over to port 8080. This enables a much better way to deploy applications in a secure fashion, and it also enables us to build features such as native Connect integration. And so with the next release of Nomad, we also now have native Connect integration. What that looks like is, say we have a service for Redis, and we want Redis to accept connections over Connect. We just define the one stanza below that says Connect and Sidecar service. They're empty, but the existence of them says we want to use Connect, and we want you to set up the sidecar automatically for us. We don't want to have to manually deploy the sidecar. We can't talk the protocol natively. So having these two things, Nomad will automatically deploy that sidecar. And then on the side that wants to connect to the application, we have something similar, but in this case, we also have to say what we want to talk to. And so we're saying we want to talk to the Redis server, and when we talk to port 6379, please route it to the service named Redis cache using Connect. Visually, what this looks like is that we have two task groups, the API group and the Redis group. And with the Redis side, we've automatically injected a proxy to accept connections. And with the API side, we've automatically injected a proxy in order to establish connections to upstream services. At the bottom of this is all just base Connect. So you still get the same encryption, intention enforcement, etc. And if you were using Nomad with other systems, such as EC2 or Kubernetes, then this would work between those services as well. And so the native Connect integration utilizes the new network namespace feature that's available, and the intentions are still managed directly in Consul. So while you could define whether you want to receive connections and who you want to talk to, whether you're actually allowed to do that is still enforced directly within Consul. So you create your intentions, say web could talk to DB, etc. Other features that are not networking related that we're really excited for in Nomad are host volumes and a new file explorer in the UI. Host volumes enable volume sharing between multiple groups using files that are already on the host. So in this case, we're mounting some certs that we had directly into a task group that we've provisioned directly onto the host. So you could imagine that these certs, they're sensitive information, they're secret, they got provisioned onto the machine out of band in some other way, but we could still make them available to our Nomad tasks. And in a future version of Nomad, we're also going to enable all of the network storage plugins, so we could have additional volumes as well. For the File Explorer, Nomad has a great UI, and we've shipped the ability to browse the files of any allocation in Nomad directly in the UI. So you could browse it just like a file system. When you see a file, such as a text file, you could read it directly in the browser. If it's something like a log file that's continuously updating, you could also tail it in the browser and see it live update just without refreshing the page. And when you look at media, it renders it directly there, so you don't have to download anything. It shows up directly in the UI. And so using this functionality, you could click around all your applications, and if you have permissions, you could see any of the files in there, log files, debug information, data, etc. All of these features, from network namespaces, the native Connect integration, host volumes, and the new File Explorer UI, are open source and available in Nomad 0.10, which will be coming soon. And so these are some exciting new features in both Nomad and Consul. We also have a lot of updates for Vault and Terraform, but so that you could have coffee and have some breaks, I will point you to other talks for those. So for Vault, if you're interested in Vault, please see Jeff Mitchell's talk tomorrow. He will be giving a Vault update about recent features as well as some new stuff that we've been working on. And if you're interested in Terraform, we have multiple talks for you. The opening keynote tomorrow is from Paul Hinsey, who's our Senior Director of Terraform, and he'll be talking pretty much about all the various things that Terraform has been up to, which is a lot. And then today, if you're interested in Terraform, we have 2 talks, one by Kristen, who is an excellent core engineer on Terraform, worked a lot on Terraform 0.12, and so she will be giving a talk on Terraform 0.12. That's today at 11:30. And there's also a talk by Chris, who is the lead in charge of our Sentinel project. And so Sentinel is our way to do policy enforcement on all our projects, but he'll be talking about Sentinel focused on Terraform, and that's also today. So please look at these talks if you want to hear updates for our other projects, and have a great day. Thank you very much.